Hi, this is a chemistry video on calorimetry, and I've been following the basic order of chemistry, the central science by Brown, Burston, LeMay, and Murphy. And like I said, this section is on calorimetry. We are in chapter 5, which is on thermochemistry, which is the chemistry of heat. All right, so we've been talking in the flow of these sections about H, enthalpy, and delta H is the change in enthalpy. And so how do we measure this change of enthalpy? Well, it can be determined by the flow of heat that takes place during a reaction. Now, thankfully, enthalpy is a state function. What that means is it doesn't matter how we get from point 1 to point 2. You can go this way and go this way, but when you measure the difference in heat from here and here, that's going to be the same no matter what path you take. So that helps us out. Enthalpy is a state function. The measurement of this heat flow is called calorimetry. You can see meter, measure in there, and calor, heat in there. So it's the measurement of heat, calorimetry. And the instrument we use to measure this change in heat is a calorimeter. All right, so we've got some basic terms there. By the way, how do you know if a reaction is going to happen spontaneously? If you drop me out of a plane, I'm going to spontaneously fall. It's just going to happen. I'm pretty sure, unless I suddenly get superpowers. And so how do you know if a reaction, we introduce these two chemicals together, is it a match made in heaven? We'll find out. Well, one of the ways to kind of anticipate that it's going to be a spontaneous reaction has to do with how large the enthalpy change is. When the enthalpy change of a reaction is large, let's say the reaction gives off lots of heat, exothermic, the heat exits, goes out. And so the item itself is losing heat in that exothermic. And so it's going to be negative joules for this thing here. It could be other measurements of heat, but I'm going to go with joules just as a picture. So whether it's a large exothermic reaction or maybe it's a large endothermic reaction, endo, where joules are brought into the subject, and it's a positive change for the subject of heat. When the enthalpy change of a reaction is large, then it will tend to be a spontaneous reaction. You're not going to have to do much coaxing to get them to dance together. They're going to dance. So that's a little side thing that was in this section. So the heat capacity of something, of a substance, an object's heat capacity is the amount of heat required to raise its temperature by 1 Kelvin, which is the same as 1 degree Celsius. We don't say 1 degree Kelvin because Kelvin is special and doesn't want to be called a degree. But anyway, the amount of heat it takes to raise the temperature of something by 1 Kelvin or by 1 degree Celsius is its heat capacity. And we can approach this from a couple of directions. So for example, we can talk about the molar heat capacity. The molar heat capacity of something is the amount of heat it takes to raise the temperature of 1 mole of that thing by 1 Kelvin or by 1 degree Celsius. That's the molar heat capacity. We can also talk about the specific heat capacity, usually just abbreviated the specific heat. This is the amount of heat it takes to raise 1 gram of that thing by 1 Kelvin or 1 degree Celsius. And these are constants. These are going to be the same for each individual substance. This is what we have nice charts for, to look these things up. So what does the specific heat look like in equation form? Well, we can put into variables what we just said verbally. The specific heat of something, S is for specific, the specific heat of something is the amount of heat, Q, that it takes to raise 1 gram mass by 1 Kelvin, by 1 degree Celsius. That's delta T, change in temperature. So there's the formula version of what we just said verbally. We can arrange it around a little and say that the heat equals MC delta T. That's the way I learned it. It has a ring to it, doesn't it? MC delta T. Q is MC delta T. Q is MC delta T, where again, Q is the amount of heat, M is the mass, CS is the specific heat constant, and delta T is the change in temperature. By the way, for water, it's about 4.1 joules per gram Kelvin. So it takes about 4.18, it's approximate, takes about 4.18 joules of energy to raise 1 gram of water by 1 Kelvin, or that is 1 degree Celsius. All right, so the last part of this section talks about a couple of types of calorimeters. What's a calorimeter again? It's an instrument for measuring the change in heat. So, first thought, is this real, a coffee cup calorimeter? Well, apparently it's pretty good. So you go to a gas station and buy a couple of styrofoam cups, right? Maybe you have a cork stopper, a glass stirrer. These are all things that are insulators. That is, they don't absorb a lot of heat. The idea is we want to keep the heat and the change of heat, especially inside the cup. We don't want it exchanging heat with the environment. And we're going to have a thermometer to measure this. So this coffee cup calorimeter is going to measure the heat under a kind of constant pressure, right? It's not increasing in pressure. And so under constant pressure, the change in heat is the change in enthalpy. The heat is the change in enthalpy. So that's a nice feature of it being a constant pressure kind of situation. All right, so since it's all staying together in here, we know that the heat of the reaction, the Q of the reaction happening inside here, is going to be of the same magnitude as the heat of the solution. It's just going to be opposite, right? So if the reaction is endothermic and it absorbs heat, then this is going to be positive, absorbing heat, and this is going to be negative. The solution is going to lose that heat, but it's going to be the same magnitude. But this will be positive and this will be negative, or vice versa. If the reaction is exothermic, then it's losing energy. This is going to be negative, and the solution is going to gain it. This is going to be positive, but it'll be the same quantity, same number, just a different sign. And so we can measure the Q of the solution. And the Q of the solution is going to be the specific heat of the solution, which usually for aqueous solutions, we're just going to assume for the sake of argument that it's like water, 4.18 joules per gram Kelvin, okay? So we're going to use the specific heat of the solution times the number of grams of solution, how much is being heated, times the change in temperature of the solution. So this is going to give us a way of knowing what the heat of the reaction is by measuring the heat change of the solution. So that's a coffee cup calorimeter, a constant pressure calorimeter. The bomb calorimeter, don't you like that? Has a ring to it. I like it. I like bombs, and this is why I like chemistry. You can blow things up. So this is a little bit more sophisticated. This is a constant volume reaction. This little thing here is called the bomb. It has electrodes in it. These are leads. This is the electricity is used to light the fire, to spark the reaction, strike the pose. This is a little cup with a sample in it. Again, these are leads to spark it up. Thermometer in the solution, again, to measure change in temperature. Nice little mechanical stir or electric stir. We spared no expense. So this is a bomb calorimeter. A lot of times it's pressurized. There's usually an oxygen valve here, to put it under pressure to get it all ready for explosion. So we have to predetermine what the specific heat of the calorimeter is, but it's the same basic principle as we did with the coffee cup calorimeter. We're going to use our knowledge of what's going on with this container in order to figure out what happens in the reaction. And so basically the heat is going to be the negative of the specific heat of the of the bomb here, of the calorimeter, times the change in temperature. And we can use a known reaction to, as it were, figure out what the specific heat is of this. Actually, it's not just the bomb; it's the specific heat of the whole thing. We can do a sample that we know what is supposed to happen with it, so that we can calibrate our sense of what this is, and then we'll be in a situation where we can find out what the heat is by the change in temperature and our knowledge of the heat capacity, as it were, of the calorimeter. Cal stands for calorimeter. So this is what we might use for exothermic reactions, or not exothermic, combustion reactions. Well, this has been a video on calorimetry. And we go on in our next video to Hess's law.